right? Now it is audible now properly.
Yes, sir.
Okay. Here we are having microprocessor architecture. I already told you that one. We are having the major component of this microprocessor, or here we are having now arithmetic logic unit. So this is arithmetic logic unit, right? Then we are having now the control unit is actually we are having now instruction registers and instruction decoder and the timing diagram, a timing and control. This is a control unit, arithmetic logic unit, control unit, and set of registers, right? So this is set of registers: WZ, PC, DE, HL, stack pointer, program counter, right? So these are all the register. This is PC, DE, HL. This is general purpose registers. These are all the general purpose registers. Stack pointer is special purpose register. Program counter also special purpose registers. Then we are having increment and decrement and address latch. We are having now, right? Then we are having accumulator. The accumulator we represent by A register. The accumulator is represented by A registers. The temporary register is internally used. Now while executing the program, then it will set the flag registers. So flag register is setting depends on the result of the arithmetic and logic unit, right? Now here we are having now that BC, DE, HL, stack pointer and program counter. This is actually B is 8-bit, C also another 8-bit. So we can have now a pair of that registers. We can do that PC pair. We can have now similarly TE pair. We can have now, then another one is HL pair. This HL pair is actually we can use for a memory address. So this is we can use as memory address. Memory address. So here we can have now memory address. Right. So memory address here, memory, how do you connect with that memory is, here I already told you that one, the memory is a, we can have now that one as, this is we are having now memory, right? So that memory is, we are having now byte addressable memory. So this is the memory we are having now, assume that one. This is connected with that address bus and the data bus connect with. So that particular memory is going to have now each location is addressable, byte addressable, right? So that is we are having now 16-bit address. 16-bit addresses we are having 2 power 16. Actually here 16-bit is, here we are having 4, 40, 80 and 16 zeros. The first address. Then we are having the last one as 16 ones. In between we are having now that address, then each location is addressable, right? So 2 power 16 bytes are there in the memory. 2 power 16 byte, right? So that is actually we are having now 6 MB, 6 megabyte memory size, 6 megabyte memory size. So 2 power 6, 2 power 6 plus 2 power 6 means here we are having now 2 power 5 32, 32 into 2 64, right? So that is we are having now 64 MB memory. 2 power 64 MB memory we are having now, right? So here the PC pair is we are having that register. Okay. Now here we can have now, this is one part is program memory, then some part is data memory. So this is actually code area, code section. This is we are having now the data section, and we can have now some stack section. We are having now stack section also. We are having now set of memory, right? Now here we can whatever program we are writing, we are going to write in the code section. Whatever program you want to have that one, we can write it in the code section. Then whatever the data we are going to store that one, that is in the data section. And the stack is used for storing and retrieving the data. Then for that we are having now the stack pointer is accompanying, right? In the stack pointer we are having that address, right? So here suppose you assume that one, the code area is starting address is 8000. Then here we are having, you assume that one, the data memory is we are having now 9000. It may be here we are having now A000. A00 is a stack section, right? Now the stack pointer is having the first address. This is the address we are having now. That address is showing now that location. Then if you are going to store some data, we can use function called instruction called push. push some A register content. So what do you mean by that one? As the accumulator content, this accumulator content is going to be moved to the top of the stack. So that's in that stack what address we are showing now. In that stack we are getting now storing that data. Then once again, then if you are pushing that another register, P register, now the P register content, whatever the data is there in the P register, the B register is going to be moved to the next location. So here we are having now B register content. Like we can have now pushing the data, then automatically it will increment the stack pointer and it will move to the next address. Increment or decrement depends on the stack representation, right? So it may be either growing in the upwards or growing in the downwards. This depends on the our configurations. It may vary upward or downwards, right? So it is incrementing that stack pointer, and whenever you are pushing the data, right? Whenever pop the data, we can retrieve the data, right? Suppose we want to push the data A and push the data B, then once again then we are calling the data is pop B, pop A and pop B. So here if you are doing that operation, so first you are pushing A and pushing B. Now popping A is we are changing that, exchanging the data and A and B, right? So for exchanging the data we can have this 4 instruction. So A is pushed and B is pushed, then once again then we are popping that A, then popping B, right? So pushing the data and popping the data using the pointer. So pointer is while pushing that increment, the popping we are going to decrement. So we can store and retrieve the data in the stack section using the stack pointer address, right? Next, the program counter is we are having now, this is a special purpose register, right? Now the program counter is going to have now, while executing that program, we are going to give the starting address of that code, load into program counter, right? Then the program counter is starting now that we are having a first instruction. This first instruction is going to be loaded into the instruction registers, right? So we are having the first instruction is LXIH, like we are having now as 9000. Then LXIH is the instruction. This instruction is going to be loaded here, LXIH. Now for that LXIH, then what sequence of operation is going to happen now through the timing control. So the timing control is giving the data to get now that 90 from the next 0 is next memory location. So that is we are having now 210090 is the opcode. So the 21 is opcode for LXI. So the 21 is loaded. For that LXIH we are having the 21. According to the 21, then it will give the control signal. Then we are getting now the data 00 is the next address, right? So the 8001 is moving now. The 8001 is having the lower byte. Now this lower byte is going to be loaded into the L. The lower byte is going to be loaded into L. Then higher byte is going to be loaded into H. So this is in one cycle. Then higher byte is loaded. So 9000 is loaded in the HL pair. Next we are having now here, if you are having that instruction is called move A comma M. A comma M is here, the M is 9000. This 9000 is going to be placed in address. The 9000 is enabled. In that 9000 we are having first data 30. Now the data is 30 is move on to the A registers. So 30 is placed here. Move on to the A register, 30 is placed here. Then we are having now that value 40 here. Then we are doing that our instruction is LX in INX sketch. INX sketch is increment that gets. So the sketch is here increment as 9001. In that 9001 we are having a 40. Now the 40 is loaded into P register. This is we are having now. Then we are having that instruction called add B. That add B instruction is going to be execute as A equal to A plus B. So that is, this is A content. Now the P content is moved to the temporary register. Then we are getting now 30 plus 40. Then arithmetic logic unit is giving control to add operation. Then that add operation is adding the data. The 70 is move on to that bus and it is placing now. The 30 is now changing that as 70. Right? Now we are going to give now that INX sketch. That INX sketch is once again, then we are incrementing that one as 9002. Then we are having that instruction called stored accumulator STA with 9002, right? So STA 9002. So that is we are having now that instruction. Then the 9002 is enabled. 9002 is enabled. Now that data 7D is placed on the data bus, right? Then it is moving the data to 9002. So that is we are having now, this is the value on that particular location, right? So whenever we are processing something, then the flag register is changing. Now as a flag registers, we are having now zero flag, sign flag, then carry, auxiliary carry, and then we are having now parity flag, right? So sign flag is, if you are having that value, the result is negative value, the sign flag will set. If you are having the result is positive value, the sign flag is zero, right? Next we are having now zero flag. If the result is zero, whatever that addition or subtraction or multiplication, whatever you are doing now, the result is zero, the zero is affect the zero flag, so zero flag is set now. Then next one is we are having carry, right? So if you are having the data ff and then another data is ff, we are adding these two data, then it will make a carry. So this is we are having now the carry flag will set. So carry flag is here we are having that 1 byte data, then more than that 1 byte data is the ninth bit, that bit is going to have now the in the carry flag, right? The auxiliary carry is used for, we are having now that one as 4 bit by 4 bit, so the total is 8 bit. Within that 4 bit, if you are having now auxiliary carry, so this is auxiliary carry. So between the 4 bit, after 4th bit, 5th bit we are adding, right? So this is 1, this is 1, we are summing that one, that is 0, then we are making that increment, that one is going to make that one as auxiliary carry. This auxiliary carry is used for adjusting the we are having now decimal, hexadecimal to decimal change. Decimal change is actually, if you are having now that value a, right? So here we are having now that value a is 10. So the 10 is here in the PCD, in the PCD form we can have now as 10 this, right? Instead of that a, we have to display the content is 10. So here we are getting now the result is a, so 0a is the result. Now if you are adding 6, right? So here in that one you are adding that 6, then what it will do now, this is 6 plus 10 16, so 16 is here we are having now 0 and 1, so we are changing that one, right? So this is how do you make that one as, here we are having auxiliary carry will set. If you are having a, then using that auxiliary carry, then it will add number 6, and if you are adding that number 6, the decimal is going to be adjusted as a PCD number, binary coded decimal, PCD. PCD is nothing but binary coded decimal, right? So here binary coded decimal means, if you are having the result is 0a, instead of 0a, that is 10. How do you get that 10 is, in that along with the 0a, the auxiliary carry flag will set. By seeing that auxiliary carry flag, then we have to add 6. If you are adding 6, then it will do now is 10 plus 6 16, so 16 is here 0 1, so that is we are having now the 16 by 15 plus 1, right? So that is we are having now that 10, that is PCD number, right? If you are having that less than 09, the 09 is less than a, if you are having 09, the hexadecimal as well as PCD is same. Here there is no need to add 6. If you are having that number 0a, 0b, 0c, right? Then 0c is 12, right? Then how do you do that one as 0c added with 6, 0c is added, 0c is 12. Then added with 6, we are getting now 18. So 18 is going to have now that one as the result. Here we are having 2 remainder and this is 1. So the 0c is represented by 12. So this is we are having now that the PCD adjustment. Then the PCD adjustment is going to happen using the auxiliary carry. So this is the auxiliary carry flag. Using that auxiliary carry flag, then it will adjust that one, right? Here this address buffer and the data buffer is, here we are placing the data in the data bus, then it will return, right? So this is address bus, so that address bus is going to have now this one, right? So this is we are having now the data and our address we are having now, right? So this is 8 bit combined together is address bus. The data bus is only that 8 bit off of that one, right? So this is actual architecture. Now you see this one, in that one we are having that extra component as serial IO control. The serial IO control is used for transferring the data from this microprocessor to another microprocessor. So we are having now serial input data, serial output data. SID is serial input data, serial output data. The serial output data is sending out the data from this processor to another processor. Similar processor you are having now. So communicate between two processor, then we can have now that communication, right? Then here we are having getting from the outside the data, that serial input data, SID. We are having the control, right? The next one is we are having now another component is interrupt controller. The interrupt control is used for the external device is connected with, the external device can communicate with that processor while executing some program, then it will make that interrupt, and it will do that interrupt service. After completing that interrupt service, it return back to that original program execution. So for that we are having now interrupt control, right? So in the interrupt we are having now the interrupt signal is receiving here through interrupt line, then interrupt acknowledgement while receiving that interrupt, then it is activating that interrupt, then it will send that acknowledgement. So interrupt is going to execute. Then we are having the now the priority of that interrupt, RST 5.5, 6.5, 7.5 and trap, right? The trap is having highest priority. What do you mean by that one? As it will have four interrupt signal. In that four interrupt signal, at a time if you are having four interrupt signal is received, then it will give the higher priority to trap and it will execute first. If there is no trap, then it will go for the RST 7.5. That also is not there, then it will go for 6.5. Then this also is not there, it will go for 5.5. If four interrupt is coming now, the first interrupt is execute the trap, next interrupt execute that RST 7.5, right? Then next one is R restart 6.5, the next one is 5.5, right? So that one at a time it will allow that four interrupt. So the priority is given by the trap 7.5, 6.5 and 5.5. So that one is here. This is actually is used for connecting that external device. The external device is going to be communicate through the microprocessor. For that we are having now this interrupt controller. The interrupt controller can interrupt while executing some program. It can interrupt and it will service on that interrupt and return back to your original program as like a function call in C. We are having that interrupt. The interrupt is going to interrupt in anywhere else within the program, right? So this is a program, then at the time if the interrupt is occur, then it will stop the execution on that level and it will give the service for that interrupt what service it is. Then we are having the operating system is having that interrupt service routine, that is called ISR. The interrupt service routine is having some set of code. Now this code is executed in that program, then while return back, then it will have now, then after completing the service routine, then it will return back to where it left and it will continue your original program. So that program is going to execute. In between one interrupt occur, the interrupt is serviced, then it return back to here and the interrupt your main program is going to continue, right? So in between we are having a context switching is going to happen now, right? That is we will discuss afterwards, right? So this is actual we are having now that 8085 architecture, right? Anybody is having doubts, you can ask now. Questions, right? Now there is a question section. If you are having doubt, you can ask now. You unmute yourself and you can ask now. Sanjay, Sweta, Sanjay,
Present, sir.
okay, you start now. Any doubts, Sanjay?
Yes, sir.
Okay. Anybody else? Madan Renuka?
Present, sir.
Is there any doubts here?
No, sir.
No. Okay. Lokesh?
No, sir. No doubt, sir.
Okay. Chaychandran?
சார் இல்லை சார்.
Haribala Krishna? Haribala Krishna? No. Dwarakeshwaran?
சார் இல்லை சார், எந்த டவுட்டும் இல்லை சார்.
Shall we go for the instruction sets now? Okay.
எஸ் சார்.
Right. Okay. Here is visible that the instruction sets. One of you.
எஸ் சார்.
Okay. We the last class we discussed about that instruction set also. Now we will continue now. Right. Here we see this one. First one as move. We are having that move instruction. Move, right? Move. We are having now. This is the destination register. This is source registers. So we are moving the data from this register to that register, right? So here we are having that the simple instruction is move A comma B. Here we are having now that P register content is going to move to A register. P register content is going to move to A register. So this is the direction. So that is we are making a copy of the P register content to A register, right? Suppose B register is already we are having the data is 10, right? Now the 10 is going to move to accumulator. So accumulator is A register. Accumulator is A register. So that A register is getting now that copying the data from B. So that is move A comma B, right? So like we can now whatever the register, right? So here we are having B, C, D, H, L, right? These are all the registers we are having now. This register content can move to A register. Similarly, we are having to P register. We can have now A, C, D, E, F, D, E, H, L, H and L, right? So that is we can move to P register. Then we are having C register. We can move that A, B, D, E, H, L. So that register content we can move. So register to register we can transfer that, move that, copy the data. That is we are using that instruction called move instruction. So this is the first instruction we are coming now. This is move instruction, right? So that move instruction is going to use for copying the data from one register to another register, and also we can move the data from memory also, right? So that is we are having now the from memory to the registers, right? So that is we are having now move B comma M. So that M means actually in the HL pair we are having an address, right? So the HL pair is we are having now address. So in that HL pair register you should have already address, right? So if suppose we are having that value is 9050 in the HL pair. So H is 90 and L is 50. Then the HL pair is having that memory address. Then this HL pair 9050 if you are having some value 45, right? Now that 45 is going to move to P register, right? So now B register content is going to make a copy of the value from the memory. Copy of the value from the memory, right? So here in that move M comma B is not possible. Move M comma B is not possible. In that direction is not there, right? So only we can get the data from memory, copy the data from memory to register. From register to memory we cannot copy, right? So So that is we are having now the first instruction. The next instruction, the similar way we are having now the next instruction is move immediate MVI. The next instruction is move immediate MVI as a next instruction. Right, the next instruction is move immediate. So that move immediate instruction, right, that move immediate MVI, move immediate instruction. Here we are having now, okay, move immediate with we are having that register and followed by we can have now that value directly in that instruction itself. We are having that value, so that value is hexadecimal value. Then the hexadecimal value is going to make a write on A register. A is accumulator, A is accumulator, right? That accumulator is having now the data 45. So whatever the data you want, then we can have in the instruction itself. We have to put now 55, then it will have that 55, right? And also then we can have now move immediate to memory location also. This is M, then followed by we are having 70. So that is the 70 is going to be loaded into the HL pair address. So HL pair is having that some address. Suppose we are having 9040 is there in the HL pair. Now HL pair is having 9040. Then in the memory location 9040, we are getting now that value 70 here. So in that memory we are writing the content 70. So that instruction is called move M, 70, right? So in that register we can have now B, 45, A, B, C, D, E, H, L, right? So we can have now, these are all the register we can have now, we can move now, right? So that is move immediate instruction. Next we are having now LDA, load accumulator. Load accumulator is LDA instruction, right? So the next instruction is LDA. This instruction are 3-byte instruction. Why it is 3-byte instruction is LDA, load accumulator. The name of that one is load accumulator. Load accumulator is instruction, right? So this is the instruction we are having now, load accumulator, right? So that load accumulator is the instruction LDA with that address. Suppose here we are having now 9030, right? So that is currently what is the accumulator content. This accumulator content is if you are executing something and we are getting now the result is 70 or something, right? It is available in that accumulator. Now the accumulator content is going to be stored in memory location 9030, right? So that address bus is going to have us 9030, then the 70 is going to copy it into the location. So this is we are having now that instruction, right? So in that memory location we are storing value 70. That is we are having now load accumulator instruction. So load accumulator here, no need to give anything, just LDA 9030. So LDA 9030 is going to load the accumulator content to the corresponding memory location. Next one is LDAX. LDAX is the instruction, right? So the address we are having now, load accumulator indirect. Load accumulator indirect. So that is we are having now, this is LDA, then we are having now LDAX. So that LDAX with we are having now PC pair register or DE pair register. So now instead of that HL pair, here we are having, this is direct address. There in that instruction itself we are having address, right? So I told you that one, this is a 3-byte instruction. So why it is 3-byte? For LDA 1 byte, then the lower byte is another. So LDA is 1 byte, right? I don't know what's the value now, that hexadecimal value, and then we are having now this the lower byte and then 90, right? So this is 3-byte instruction. Now we are having now LDAXB, right? So LDAXB is 1-byte instruction. What it will do now, in the PC pair we are having some address, right? So suppose we are having now this is 9090 we are having now in the PC pair. 9090 in the PC pair, right? So instead of that address, direct address, this is called indirect address. Why it is indirect address? So in the PC pair we are having now the address. So that one as here we are having that in the 9090 we are going to load the accumulator. The content of rest pair point to the memory location. Okay, check. This is the case, or we can use the TE pair. So we can have now two instructions, right? LDAX B or LDAX D. D means we are automatically it is TE pair. Because of this X is here, we are having 16-bit register. X mentioned that one as 16-bit. Wherever we are having that letter X, that is mentioning about that one pair. So P means P pair, PC pair. D means DE pair. So that is we are having now this X, right? Next one as we are having now that instruction is LDAX. LDAX LXI, right? LXI we are having now register pair. So LXI that register pair, right? So that is we are having now LXIH, LXIH. So that is HL pair. HL pair is having address. That address is in that address we are storing the data about the accumulator, right? So we are having now that LXIH. LXIH is actually we are having now the HL pair, right? So we are having now LXIH with the value. So that is in that HL pair we are loading the data. So load pair register. That LXI is nothing but load pair register. So H we are having now this is 9000 as here address. So this address is going to be loaded into HL pair. So if you are executing this instruction, now the HL pair is going to have as HL pair register is going to have as 9000. So the 9000 is loaded into LXI HL pair. So that LXI instruction is we are load register pair immediate. Load register pair immediate is LXI. Right? So this is we are having now load register pair is LXI, right? So that is we are having now that LXIH 2034, right? LXIH 2034, that 2034 is loaded into HL pair. So here we are having now that instruction is LXI H, right? So that is we are having now LXI H with 2040. So now the location memory is 2040. Now the HL pair register content is going to have that one as higher byte is 20, lower byte is 40. So that is we are having now. Next load HL is indirect, right? So that is we are having now. Okay. So this LHLD, right? So LHLD is doing now the instruction copies the content of memory location. So memory location pointed out by the 16-bit address into register L and copy the content of next memory location into, right? So that is here what we are having now LHLD. Load LHLD is, right? So here we are having now LHLD is here we are loading the HL pair with 2040 location and 2040 you are having some value. Then here we are having value 80. Then in the 2041 we are having that value 90, right? So the lower byte is 90, higher byte is 80, lower byte is 80, higher byte is 90. Then LHLD is doing now the HL pair is going to alter that one. The lower byte is in 80 here, then higher byte is going to have 90 here. Now we are changing the address. So this is we are having now the HL pair is loaded from address, right? So here we are having now LHL here we are having now LHL is loaded from the address. So that LHLD is loaded from the address, right? So this is actually LHLD loaded from the address. So this is the address So on that address we are having that value, so that value is going to be loaded, right? So that this is actually direct address. So the direct address, so the 2040 and 2041 is having the lower byte and higher byte. This lower byte and higher byte is loaded into HL pair, so that is LHLD, that instruction. Next we are having now stored accumulator. We are having that instruction called stored accumulator. Right. Next instruction is stored accumulator, STA. STA is stored accumulator with some address. So the we have written in program, right? So that 9002 we are going to store that accumulator, right? So the accumulator content, accumulator content is going to be store in the location of 9002, right? So in that memory we are having now 9002 is one location, right? Then accumulator, suppose accumulator result is already, we are doing something, we are getting the result is 70. In that accumulator we are having 70, that is A register accumulator, or we can call it as A register. The content 70 is going to be stored in the location of that memory as 70. So this is a memory location where we are storing now. In that 9002 we are storing now the value 70. That is stored accumulator. So that is instruction, right? Next we are having now stored accumulator with the register pair content. So this is actually we are having now STAX with B. What do you mean by that one? As in the PC pair we are having that address. Suppose we are having, this is 9005 is there, right? Now 9005 is already in PC pair. Now we are having the instruction called STAX with B. Now the accumulator content is going to be placed on the location 9005. Then if you are having value 70, then the 70 is going to be stored in the location. 70 is stored, as well as the accumulator is having that same data there itself. Now we are storing in that memory location also. We are having now that is STAX. Next one is store HLD, right? So that is in the reverse, right? So LHLD is, so here from the address and next address we are loading the HL pair. Now we are having store HLD. So now current HL pair address is going to be stored in some memory location. So 2040R is there. Then in the location 2040, we are going to store the HL pair, right? Suppose the HL pair is already we are having as 9010 in the HL pair. Now this HL pair content is going to be copied here. The lower byte is 2040. Next to the 2041 we are having now 90. This is we are having now stored HL pair with direct address. So stored HL pair with direct address, SHLD. SHLD is stored HL pair in the direct address HL, right? Next we are having now that instruction called exchange H, right? So that is we are having now the HL pair and the TE pair is exchange, right? So that is exchange HC. The instruction name is exchange HC. Okay. The instruction name called exchange HC, right? So that is the instruction. We are having now that one as exchange HG, right? So that is we are having now HL and TE pair, right? So in that HL pair, if you are having that one address, this is if you are having now 9020, then DE pair is we are having some other value, right? So that is we are having now 9040, or if you are having now this is 8040, right? Then here what it will do now, using the temporary registers, then we are exchanging now, right? So this is 40, this is 80. Now here we are having this is 20, this is 90. So we are exchanging the HL and the TE pair. Exchange HC is itself instruction. So we won't show that one, right? The HL and HL and T. It is implied that HL pair and TE pair is exchanged. So the instruction is just exchange HC only. There we don't show that B and D, right? So that is implied automatically. It will do now that the exchanging of HL and DE pair, right? Next one is here we are having now stack pointer and HL, SPHL. The next instruction is called SPHL. Copy the HL registers to the stack pointer. To the stack pointer. Okay. So here SPHL, right? So that is yes. Next instruction is we are having now that instruction called SPHL. SPHL. So here the HL pair content is going to be stored in the SP. HL pair content, right? To copy to the stack pointer, right? So that is stack pointer is there. Here HL pair is there. To this is HL pair register. Then in the below which we are having program counter, then stack pointer. Now in the stack pointer, we are having whatever the HL pair currently now. Suppose you assume that one 8040 is a HL pair now. Now this 8040 is going to move to in the stack pointer. So the stack pointer is 16-bit address. So the 16-bit address currently, if you are executing this instruction, here we are having now 8040 is copied into from the HL pair register to stack pointer. So that is SPHL. So current HL pair value is going to be copied into 8040. So that instruction called SPHL. So SPHL is we are having now the HL pair register value is going to be copied into the stack pointer. Next, XTHL. Exchange HL with the top of the stack, right? So here exchange HL with the top of the stack. So that is XTHL. The next instruction is XTHL. XTHL, right? So XT is nothing but stack. You assume that one. Stack T is top of the stack, right? So the T is the top of the stack. So we are having X is actually pair of register. Then we are having now the HL, right? So that is we are having now the HL register value is exchange between top of the stack pointer, right? So that is stack pointer is showing one address. The stack pointer is showing one address for suppose you assume that one A00. This is a stack pointer now currently. Then HL is having now that value as 9040, right? Then the stack pointer is showing that location is A000, right? So in that stack pointer we are having some value, and A001 we are having A001 we are having some other value, right? So currently the stack pointer is A001. Then here we are having now that this is we are having 80, this is 30, 8030, right? Now we are exchanging the HL pair with top of the stack, right? So this 80 is here we are having now the exchanging now, right? So 80 is going to have this one as 40 exchanging now. This is the exchanging, right? So that is this 80 is going to come here, right? The 40 is 90 is going to come here, right? Then here 40 is exchanging here, then 30 is going to move to here. Then after executing that one, so exchange the top of the stack with HL pair. So that is here, right? So this is the exchange. The exchange is that X, right? That and also here we consider as pair register, right? So this is HL pair. So the HL pair content is moved to the top of the stack, right? So that is here now XTHL. So what stack pointer is showing now? The stack pointer content is the exchange with H, and stack pointer plus one content is going to exchange with the L. Next instruction is push instruction, right? So we can push all register content, right? So here we can push A register, P register. Next instruction is push. The next instruction is, we call it as push instruction. So we can do that push instruction. We can write push instruction with here A register or single register, right? B register or C register, D, E, H, L. So whatever the register it may be, right? So this is register pair, right? So that is register pair. Push with register pair. B, okay. Register pair. Here we are having now the registers only, right? So P register, right? P register content is going to be stored. This is A register, P register. So that is not register pair. So just we are having now the P register, right? So P register and A register. 1 minute. B, D, H, A. A, okay. That one is here push. 1 minute. Sorry, this is actually we are storing now as we can have that instruction as push A and push D, then push H, right? A, D, H, B, A, B, D, H, A, B, D, H, right? So push A, push D, push D, push P, push H. So these are only possible instructions, right? So the A register content along with the flag register content is going to be stored as 16-bit. A register content and flag register content. A register content and flag register is going to be pushed into the stack, right? So the stack pointer is showing some address. So that is stack pointer is, suppose we are having now this stack pointer is 9080, right? In 9080 we are storing A register content as well as the flag register content, right? So the flag is having some set of value, right? Sign 0, that is, I can show that one. Now you see this one. So this is the flag register, right? The flag register is having now, this is 8-bit. The 8-bit first one is sign, then 0. This is dummy, right? So there is no use. Then auxiliary carry, then no use, then parity, then no use, then carry, right? So this is actually sign, 0, auxiliary carry, parity, and carry, right? So that is we are going sign, 0, auxiliary carry flag, then parity flag and carry flag, right? So this is combined together as 8-bit. So this 8-bit value along with that push to the A is going to be pushed into the storage, right? So that is we are coming now through the stack pointer. The stack pointer is automatically increment to 9082, right? Automatically increment, no need to increment that one, automatically increment. Next we are having the instruction push T, means the TE pair is going to be pushed. Next instruction is push TE. If suppose you assume that one, right? We are writing the instruction push TE. Now the TE pair is going to be pushed into the stack, right? Then 90804 is where. Next one is if you are having push P, then we are having now PC pair. The PC pair content is going to be stored in the stack. Next we are having cache, then HL pair content is going to be stored in the. So all register content is going to be stored in the stack through the instruction called push A, then push B, then push D, push H, right? Then push out. That's all. So this is the case, right? Now here we want to get once again the return back the data. Then you have to pop in the reverse order, right? So pop H, pop D, pop P, pop A. Then whatever that register content is going to be restored through the pop instruction. So push and pop is used for using the stack pointer address. We are pushing and popping the data. The stack pointer is while pushing now automatically moving to next location. So that is we are considered as top of the stack. That is we are having now push and pop. Right. Next one is we are having now that in and out instruction. In and out instruction, right? So the out instruction is used for Now the out instruction is used as, here we are having the port number, right? Port number we can have now between 00 to FF. What it is actually, from your processor to external device. So we are having one external chip. Through to the chip you want to send some data, right? So this is your processor, this is some other machine or something, then you want to transfer the data through that port. Now you are giving the this is connected with that one using port number, right? So port number is, suppose we are having now this port number is 0A is a port number. Then we can give it now that the instruction is called out 0A. What it will do now, the accumulator content is going to be move to the particular device, right? Then another device we can have now, that device is address is 0B. Now you want to send the data to that particular device, then you have to write the instruction called out 0B. Then our processor is selecting that device, then transferring the data to the particular device. Like we can connect with around 256 device, we can connect through the processor, right? So another devices are connected with the 256 devices, then we are giving the unique address for each device. Then using that out instruction we can transfer the accumulator content to each and every output devices. Each and every output devices we can transfer the data, right? So this is we are having a 0A, 0B, 0C, like we can have now the address, right? So the last one is, suppose we are having this is FF is the one device, then we are transferring the data through FF, right? So that accumulator content is going to be transferred, right? Then here we are having in is used for in the reverse. We are getting the data from the external device to accumulator. So in 0A is giving now this device is having some 8-bit data. This 8-bit data go back to accumulator. So we can read the data from the external device using in instruction. In instruction is used for reading the data from outside world. The outside world is having the port number for each device. Then through the port number we can get the data from outside to your processor accumulator. So that is we are having now that in and out instruction. So that is, here you see this one out F8. So the device address is F8, then to the device we are transferring the data. The in 8C is, from the 8C is another device, it is transferring the data into your processor. That is in instruction. Another 10 minutes, then we will stop, then we will continue by next coming classes, right? Next one is we are having that arithmetic. So these are all we are so far we have data transfer instruction, right? So up to now we are having transferring the data from one location to another locations, we are transferring the data. So these are all so far we have discussed about the data transfer instructions. Next coming instructions are arithmetic instruction. Arithmetic instruction, we are using that add instruction, right? So we are having that instruction called add instruction. So the add instruction, you see that one here, add A, add B, right? So add B, add A also is possible. So this is actually add A, add B, add C, add D, right? Then we are having add E, add H, add L, then next one is add M. This is actually what we are having now. Within that one, that one accumulator is implied. Accumulator is implied. So the result is actually A equal to A plus A. So that is equal to 2A. Suppose you want to have that value is multiplied by 2, just you are calling the add A. So what it will do now, the A value is paired and then we are summing these two, we are getting now that one 2A. So that is we are having now the A register content and A register content. We are adding these two, right? So accumulator content is copied into temporary registers. Then it will do that add operation in the arithmetic logic unit. Then we are giving the result in the once again that accumulator. So that is we are having now A equal to A plus A. So this is add B is nothing but A equal to A plus B. Then C equal to add equal to A plus C. Then A equal to A plus D. A equal to A plus E. Here we are having now A equal to A plus E, A H. Then A plus A equal to A plus L, right? Next one is A equal to A plus the Ketchel pair address content. So the Ketchel pair address is having now the memory location, right? So this M is nothing but the HL pair address content is getting the data from the memory, and we are having the accumulator content. This is added and the result is going to be placed on once again the accumulator. So that is we are having now the last instruction, add M. So these are all the possible instruction for add operation, right? Next one is add with carry. So all are the same one. Instead of that AD with we are having now carry, ADC. So ADC is the same instruction we can have now. Instead of that add we can have the ADC here, right? So in that AD you replace it by ADC. What do you mean by that one as plus the carry content, carry flags, right? So the carry flag is added. Carry flag is if you are having one, then this is added with the carry flag. This is add with carry, add with carry. So the carry flag is, if suppose carry flag is 0, then there is no add, right? The carry flag is 1, that carry flag content is added with, right? So that is if you are having that 16-bit addition, right? So first 8-bit addition, then while doing the 2 8-bit addition, then we are getting now the result, then it may make a carry. Then next 8-bit addition, then while doing that one add these two and we are making a carry, the 1, and we are getting now the 16-bit addition. So we are 8-bit addition doing now, then it may carry, then the carry is added, then once again then another higher byte is added, we are getting now the result. Then here also we may have some carry. So the result is here, this is 8-bit, this is 8-bit, 16-bit, 8-bit, 16-bit, then we are having now one carry also. The total 17-bit as result. If you are having now this 16-bit plus 16-bit addition, we are getting now the result is 17-bit. So that one is going to have as carry flag. This one, right? That is add with carry, right? Next one is add immediate, ADI. So that is we are having now ADI, add immediate is here we are having now the accumulator content is added with that direct value, add immediate 40. So that is equal to A equal to A plus 40. That is we are having now add immediate instruction, ADI. So directly we are giving now one data from instruction. So from the instruction itself we are having the data. The data is going to be added with accumulator and the result is we are having in accumulator, right? Next one is add immediate with carry, ACI. Add immediate with carry, ACI, right? So this is A plus 40 plus carry. That is add immediate with carry, ACI. ACI instruction is add immediate with carry. Then next we are having now double add. So registered pair, right? So here we are having now DAD. DAD is actually we call it as double add, right? The instruction called DAD, right? Double add, DAD, right? Double add with B. So that is we are having now current. Here you have to consider now the HL pair is act as an accumulator. So the HL pair with the HL pair content plus TE pair, BE pair, sorry, BC pair, PC pair, DAD B or DAD B D pair, right? Then DAD once again that H also. right? So that is we are having now HL equal to HL plus HL. So 2 times of the HL. We are having HL pair, right? That is equal to H equal to H plus H. HL plus HL. HL equal to HL plus HL. That is DAD H. Right? DAD D is HL plus DE. Then DAD B is HL plus PC. So that is we are having now that double add intersection. Right? Today we can stop here. We can continue by next class. If you are having doubts, you can ask now. Hello students, have you understand now?